Okay, this is the review session for exam number 3, so go ahead, ask questions. I'll cover anything you guys want. Yeah.
I see a first order and second order plot, graph plot.
Yeah? Oh, you want to see one? Yeah. Okay, so so what's the difference between first order and second order? What are the rate equations? So first off, first order is right? Or something like that, right? That thing is still first order. We don't really know how to plot this. But if you take the simple expression for rate, and if you plot, for first order, let's say A of t, B of t. So our equation that we're going to use, or our chemical equation, A plus B goes to C. So we have log A of t. What's A sub t mean? The concentration of A at time t equals negative K divided by 2.30 times time plus log. What's A0?
Concentration at time 0.
Concentration of A at time 0. So what's the linear plot look like for first order? So what are we going to plot? Log of AT. What's on the bottom axis? Or x-axis? Time. Is log of AT going to go up or down as a function of time? Down, right? Given this, right? What's the concentration of C going to do as a function of time? Go up. Okay, why is it a straight line?
Because we linearize.
Y, whoops. Y equals M X time plus B. So what's the intercept? Log of A0 is the intercept. What's the slope?
Minus K. Oh, well, K.
Minus K over 2.3. Yeah?
If you use natural logs, can you get rid of the 2.3?
Yes.
All right.
So this is 2.303, so that goes away if you use natural logs. So first order, the key parts of it are m plus n is 1. That's the definition of first order, right? No other definition of first order. And then this plot is very special, and it's derived from this equation right here. So if you know the rate equation or the change of reactants as a function of time, let me find a pointer here. If you know the change, how the reactants change as a function of time, you can just think about how you linearize this equation. And so this thing right here tells you how you should make the plot. So it's no secret how this plot is constructed. You just need to look at this equation right here and figure out y, m, x, b. So that's why linearization of equations was important in order to figure out what's going on here. Yes.
So if you were given like a data table,
Yep.
would you plug in the numbers to that equation, and if it was linear, that it would be first order?
Exactly. Yeah, so that was the gist of that homework problem, right? Is I gave you a data table, and you plotted ln of at versus time, and you plotted log of 1 over at, sorry. 1 over at versus time, and log of at versus time. One was straight, and one was curved. And so because we're using this linearization technique over here, the only one that fits this equation, because this is line, is the one that works. So that's how you decide between first order and second order. Yes?
Okay, since the rate equals K times the concentration of A to T naught, B, would that be still the same rate for B as A? Because A and B are both, so you have rate equals K?
Yeah, well this one, I mean, so the only thing you need to know about first order like this is still first order because you have M and N. But this one is more difficult to analyze than this right here.
Okay, the rate up there doesn't tell you anything about B at all? I mean, wouldn't B have the same rate as A?
Here?
Yeah.
Oh, this is a good, okay, so if the rate law was this, if the rate law is first order in A for this reaction, what's the rate law for B? 0th order. Why? Because the rate doesn't depend on the concentration of B in this equation, right? So we can say if this is the rate law, we know that the rate is first order in A and 0th order in B. If this is the rate law, we say it's half order in A and half order in B. And so you're not going to have to analyze these sorts of situations. But you should know that this one right here is first order for A, and 0th order for B, given those two parameters.
Okay, then C is inverse.
C is a product.
Product, yeah, a product. But if the reaction went backwards.
Yeah. So okay, if the reaction is backwards, okay.
That would be the inverse rate. Wasn't there something though?
Yeah. So this, what rate constant is this?
That was the forward.
K forward.
Okay.
What rate constant is this?
K backward or reverse.
Reverse.
Okay.
What's the relationship between KF and KR? KEQ is K forward over K reverse. Or do I have that backwards? Which is KF over KR. Excuse me. Yeah, I've got it. So it's not this. So Charlotte, I think you wanted to say that KF equals 1 over KR.
Yeah, that's not right.
Don't do that.
Yeah, okay. I wanted to know what A and B and C were in relation to the whole thing. You know what I mean? So B would be the 0th order, A would be the first order, and C would be equilibrium constant.
Well, if we're talking about if we're talking about KF, C has nothing to do with it, right?
Well, yeah.
Yeah.
Yeah. But if you ever, if there was another part of the question,
If there was another part of the question, then I asked you about KR. Yeah.
Yeah. Okay.
And I might ask you, what's the real? I could give you the forward rate constant and the reverse rate constant, and say, okay, what's the equilibrium constant? Or I could tell you what the equilibrium constant was in the other one. But you'll have to figure out, just because you have this reaction, right, doesn't mean that it's second order. So having A plus B go to C doesn't mean it's second order. So you need some data to tell what the reaction order is. Just like C goes to A plus B, what are the possible reaction orders for this one? 0 first, second, it could be anything, right? Until you have data or until you have some information that tells you what the change in concentration is with time, you don't know. Yeah?
Could you go over what a parabolic order rate is?
Sure.
Thank you.
Wait, I haven't covered second order yet. So this whole thing, remember, this equation means first order. And it's linear, and this plot means first order. If the concentration as a function of time doesn't fit this equation or doesn't fit this plot, the reaction is not first order in A. Okay? So second order, whoa, sorry. No. Just so you don't get confused about A, B's, and C's, A plus C goes to M. Perfectly valid thing to do. So we know that the exponents are 1 here. It's the definition of second order. If we look at the rate law for second order, you see that 1 over equals, oh, sorry. So that's second order reaction here, but this reaction is actually written for rate equals K. So this is second order in A. And this is this one is actually, what order is this in A? First order in A. Yeah, so we could analyze the concentration change of A using first order kinetics. But the total reaction rate is first order in A and first order in C, so this is a second order reaction. Now this one is second order in A,